Good afternoon, students. We want to continue with our previous lesson that we discussed on organic chemistry. In our previous lesson, we discussed about the introduction of organic chemistry. We discussed about alkanes, the naming of alkanes, the nomenclature, and remember, you should remember those rules. We also discussed the structural formula, condensed formula, and also the molecular formula. So ensure that whatever we discuss here, you go and review. Remember, we normally have a formula for reading these terms and mathematics. We have R and 3Q. You read questions, then you review or you visit your work. So ensure that you revisit for you to go with my flow. So today we want to discuss about preparation of alkanes, and this is also where most of the questions will come from. So preparation of alkanes, alkane in the laboratory. So we normally have a setup that is used to prepare these alkanes, and we normally prepare alkanes with the respective alkanoate and soda lime. Soda lime is specifically sodium hydroxide. So when you hear the word soda lime, that is sodium hydroxide. So like for example, they can tell you how to prepare methane. How will you prepare methane? We prepare methane by using sodium ethanoate and plus sodium hydroxide. Sodium ethanoate plus sodium hydroxide. So we normally prepare a respective alkane, like for example methane, by adding one carbon to one of the reactants that will be used to prepare. Like for example, ethane use ethanoate, methane use ethanoate, ethane will use propanoate. So we add one carbon and OH. OH means we have oxygen that is added. So we have a setup here. Like for example, here it is now the preparation of methane. So methane is prepared by reaction of sodium ethanoate and soda lime. Soda lime is sodium hydroxide. Sodium hydroxide. So we normally have heat. So this is now a flask, round bottomed flask. You might be at this apparatus that is used. This is a round bottomed flask. So we mix this soda lime, that is sodium hydroxide, and sodium ethanoate to prepare methane. This is now preparation of methane. This is preparation of methane. Preparation of methane. So we have used methane to represent all alkanes, and they are prepared in the same way. So methane, we use sodium ethanoate plus soda lime. This is a round bottom flask. So when you heat, the reaction will take place. We are going to collect sodium carbonate, and there is what we call effervescence, sodium carbonate and methane that will be produced. So this is a beehive stand. Take note of this one. You might be asked to give the name of this apparatus, a beehive shelf or a beehive stand, but this is a beehive shelf. Then it is also collected over water, and it is because it is slightly soluble or it is insoluble in water. And this is a trough. Then this is a gas jar. Then we have methane collected here. So the mostly question that is asked here is to write a chemical equation for the reaction between sodium ethanoate and soda lime. So this is now the reaction that is taking place in this particular case. So like for example, so here sodium ethanoate, we start with the gas itself, C, H3COO, then Na, then plus sodium hydroxide. We are going to get sodium carbonate plus methane CH4. Now I want to explain this equation for you to know very well. So this solid soda lime, sodium hydroxide is also solid. Then this is a gas, this is also a gas. I want to explain this equation here. We are now preparing alkane. Before heating this, the flask, these reactants are in solid form. Sodium ethanoate is written in this form. We start with the name of the organic compound, that is sodium ethanoate. Two carbon atoms, then ethanoate. It means that it has two atoms of oxygen. You can see have two atoms of oxygen. Ethanoate. It means that it has two atoms of oxygen. Sodium ethanoate, then plus sodium hydroxide. You get sodium carbonate. So this sodium combines with these three oxygen. Carbon then combines with the three oxygen to form a carbonate, sodium carbonate. Then plus methane. So this hydrogen here will come and combine with this a methyl group to form methane. So this is now a reaction. So before heating this, they are in solid form. Sodium ethanoate and sodium hydroxide, they are in solid form. So now after heating, they now become in a liquid form, and that's why the symbol states here, you see, in solid. This reaction cannot take place without heating, because the reactants are in solid form. So when you heat, they become in liquid and they react to give methane gas, which is collected here. And they must actually explain the reason why methane gas is collected over water method. This is because it is slightly soluble in water. It cannot dissolve in water, and therefore it is collected over water. You can also collect ethane using the same way. So here we just replace ethanoate with propanoate. Are we together? So ethane is collected by using sodium ethanoate, sodium propanoate. So propanoate, it is 3 carbon, so that is CH3, CH2, then C, then 1, 2, then carbon and sodium, then plus sodium hydroxide. Now we are going to get sodium carbonate, then plus ethane, CH3, CH3. That is how we prepare sodium. We prepare ethane. It is prepared by sodium propanoate plus sodium hydroxide to produce this product, and ensure that the equation is balanced. This is solid, gas. Ensure that the equations are balanced. In our case here, the equation for the first equation, it is balanced, and also the equation, our second equation, the equation is balanced. So that is how we normally prepare alkanes. We use like for example, they can draw for you this one, and then they ask you some questions for you to answer. So when you want to prepare propane, you use sodium butanoate plus sodium hydroxide to get sodium carbonate plus propane. When you want to prepare butane, you use sodium pentanoate plus sodium hydroxide to get the product. And then remember, this sodium here, I say that this is valent 2. Sorry, this is valent 2 here. Carbonate is valent 2. I'm sorry for that case. Carbonate is valent 2, so we put here 2 for equation to get to be balanced. So here, so two sodiums come, then these three oxygen combines to form a carbonate. Then the remaining hydrogen will come to form a methane, an ethane. Like for example, when you want to prepare propane, you use sodium butanoate. So CH3, CH2, CH2, then C, then OO, then Na plus sodium hydroxide. You get sodium carbonate plus butane, CH3, CH2, CH2, CH3. That is now butane. So this equation is also balanced. So that is how we prepare alkanes. You use you identify the name of the alkane that you want to prepare. When it is, like for example, alkane, for example, ethane, you add one carbon to form a propanoate. So you take sodium propanoate plus sodium hydroxide to prepare what? Prepare ethane. So you identify the name of the of the alkane you want to prepare, then you add one carbon, then you add more oxygen, form an OH for you to prepare. So that is now how we prepare these alkanes, as simple as that. There's no more question that we normally ask there. The place here is carboxylation reaction. That is the type of reaction that is taking place when this reaction takes place. That is carboxylation. Take note of that. You might be asked that question. And so the equation you might be asked the equation. Then I have also said you give a reason why this method is used to collect the gas that is slightly soluble in water. Then also you explain how these gases, like for example methane, when you place methane in bromine, what will take place in presence of sunlight and also in absence of sunlight. There is only one reaction of which you want to discuss. We'll understand at this particular point when we go to chemical properties. So that is now how we prepare these alkanes. Very fast, let's move to physical properties of alkanes. 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 So these alkanes, they are non-poisonous, colorless gas, slightly soluble in water, and therefore they are collected over water. And they are soluble in organic solvents such as ethanol and tetrachloromethane. Then it's less than air. So these alkanes, they normally differ. Like for example, methane, ethane, propane and butane, they are gases. But from pentane up to decane, those are liquid. Then from number 11 onward, those ones are solid. So this one, they are colorless. That is, those are just common physical properties. Number one, they are colorless gas, and they are non-poisonous. So number one, colorless gas, and also non-poisonous. Number two, slightly soluble in water. That is also a physical property, soluble in water. Then we can also talk of they are soluble in organic solvents. Take note of this one. They are soluble in organic solvents. Soluble in organic solvents. So they are soluble in organic solvents. What are organic solvents? These are examples of the organic solvents. Those are ethanol, tetrachloromethane. So they are soluble in those organic solvents like ethanol, because of their bond that exists between the atoms. The bond that exists between the atoms. So they are soluble in organic solvent, but not in water. Then we have another one like methane, TC, less than air. So this is now the basic of physical properties. Colorless gas, lightly soluble in water, and also soluble in organic solvent. However much we are saying that they are colorless gas, we also have liquid. Like for example, so here we say a colorless gas like methane. We give an example: methane, ethane, or give from number 1 up to 4. That is from methane to butane. Then the liquids, they are from number 5 up to 10. Then solids from number 11 onwards. Didecane, tridecane, as we move on. Let's move to chemical properties. Physical properties, that one is simple. Chemical property, that's where we might be asked questions. Chemical properties of alkanes. Chemical properties of chemical properties. So the first chemical property, they burn in oxygen to produce carbon dioxide and water. Any organic compounds, when it burns in oxygen, they produce carbon dioxide plus water. Like we are using methane as our example, plus oxygen, it produces carbon dioxide and water. So any alkane, when it burns in oxygen, it produces carbon dioxide and water. It produces carbon dioxide and water. So when it burns in excess oxygen, so this one talking about it is excess, it produces carbon dioxide and water. The equation is balanced. Here you have 1, 2, 2. Here you need to place here 2, then here 2. Our equation now will be balanced. So this is now in excess oxygen, but in limited supply of oxygen, excess, limited means kidogo, it produces carbon dioxide plus water. Carbon dioxide plus water. Our equation is balanced. Here you place here 2. Here 2, oxygen 4, hydrogen 4, oxygen 3. Then, so when you place there 2, let's place 4, 2, 3, 2. Here it is 4, 2, 3, 2. Our equation is now balanced. So take note of this one. In excess supply of oxygen, alkanes will react with oxygen to produce carbon dioxide and water. But in limited supply of oxygen, alkanes react with oxygen to produce carbon dioxide and water. Then there is also another one. We call it substitution reaction. There is another physical property. Nimesahau. When it burns, not that one. When it burns, it's a chemical property. When it burns, it produces a blue flame or a non-luminous flame. So that is a chemical property. When it burns, it produces a blue flame. It burns in oxygen to produce a blue flame. A reason for that one, it is saturated. Are we together? That is now the reason. Give a reason why alkanes burns in oxygen to produce a blue flame or a non-luminous flame. You say alkanes are surrounded with 4 bonds and therefore they are saturated. So when you place a spatula full of alkanes like methane, on a wooden on a glowing splint, it produces a blue flame. It lights producing a blue flame or a non-luminous flame, because alkanes are saturated. Then the last reaction is what we call substitution reaction. It undergoes what we call substitution reaction. Substitution reaction. Substitution reaction. Substitution reaction. So substitution reaction, this is a reaction whereby alkanes undergoes in presence of UV light. Alkanes normally undergo in presence, normally react with a halogen in presence of UV light. So substitution reaction, it's a reaction whereby alkanes react with a halogen in presence of a UV light, that is ultraviolet light or sunlight, to produce it normally produces an acid, hydrochloric acid. Then one hydrogen is substituted in that alkane. Like for example, methane reacting with chlorine in presence of UV light called sunlight. That is the condition there. So for example, methane reacting with chlorine in presence of UV light. UV light. Is there a catalyst to produce chloromethane, that is CH3Cl plus HCl. So when you draw a structural formula, you will find that one hydrogen is substituted. The function of this light is to break the bond between this chlorine for it to be substituted in this reaction. Like for example, when you write here a structural formula here, you'll find that one hydrogen is substituted with the chlorine here, and that chlorine reacts further with that hydrogen to form hydrochloric acid. And that's why the reason the function of the UV light is to break the bond between chlorine atom, so as to form chlorine element, chlorine, for it to be substituted in the reaction. So this is now a structural formula, C of methane. This is hydrogen, then plus chlorine. Here we are assuming that UV light has broken, has not yet broken, because this UV light need to break this bond here. This is what we call covalent bond here, for it to react with it to be substituted. Then here we are getting this one. This is chlorine, then hydrogen, then plus HCl. So this is what we call substitution. This chlorine has substituted one hydrogen here. Let's say this one, imertor. That's what we call substitution. And the hydrogen has further reacted with one atom of chlorine that was remaining to form hydrochloric acid. So this chlorine here has gone here, and this chlorine has reacted with this hydrogen. This is what we call substitution reaction. And this reaction cannot occur without the presence of UV light, because UV light is there to break the bond between chlorine atom for it to be substituted. Also, ethane can also undergo the same reaction, or the same methane. This chloromethane. So the name of this product is chloromethane. Are we together? Chloromethane. The same chloromethane can further undergo substitution reaction, UV light, to form CH2Cl2 plus HCl. This is also the same as substitution reaction. UV light has broken. So when you write the structural formula, because in an exam they might ask you to write the structural formula. The structural formula will now look like this. Hydrogen, then plus HCl. So this is now 1,1 dichloromethane. 1,1 dichloromethane. When you remember the nomenclature of alkanes, and that's why you cannot move a step without understanding the previous class or the previous concept. These are 1,1 dichloromethane. Or since it is on first carbon, just say dichloromethane. There's no need of saying 1,1. You can just say dichloromethane. The same dichloromethane can also react with the fluorine. The same dichloromethane. So here it is 2, then here 2, then here it is CH, then Cl3, then plus Cl2. We get CH. Here was what? 3. The same this one now. Sorry. CH2. Yeah. Here it is 3. Sorry for that interpretation. Here it is 3. This one was 3. Then only 1. Then this one CH2, then Cl2 to react with this chlorine to produce CH, then Cl3, then plus HCl. This one is trichloromethane plus HCl in the presence of UV light. So in an exam, they can give you an alkane, and then they want you to write all the equations or the steps that will take place in substitution of methane in presence of UV light using chlorine or using any halogen. When you can replace it with bromine, iodine, the choice is yours. What you need to consider is the UV light. So that is now the steps of substitution reaction. This is 3 marks in an exam. Methane reacts with first chlorine to form chloromethane. Then chloromethane reacts with another chlorine atom to produce dichloromethane. The same dichloromethane reacts with another chlorine atom, and until chlorine is hydrogen is substituted fully. Until hydrogen is substituted fully. For this one, you can also write C. The last step here, it is CH, Cl3, then plus Cl2 to form CCl, then plus HCl. That is now the last step until all hydrogen is substituted in this reaction. Until all hydrogen is substituted in that reaction, then you ensure that all the reactions are balanced for you to get a mark. All the equations are balanced. Then you place the state symbols. Methane is a gas, chlorine is a gas, this is a gas, this is an acid, but it is in gaseous form. All of them are gases. So that is now the substitution reaction, and that is where most of the question will come. This reaction, preparation, substitution reaction, and also some of the physical property, and also when it burns in limited supply of oxygen, what will you observe when methane? We said that is a blue flame, and also can talk of a non-luminous flame. Let's move to the last part, uses of alkanes. Uses of alkanes. I advise you about on uses. You name the name of the alkane, then you say it's used. You don't just say are used in fuel, are used in, no, name the alkane itself. Like for example, methane is used as a fuel, you will get a mark. Are we together? So just say methane or gaseous alkanes. Like for example, methane, ethane, all of them, all gaseous alkanes are used as gases. But you can just take one. Like for example, methane, you say methane is used as a fuel. Methane is used as a fuel. You get a mark. Then manufacture of carbon black compound, which is a component of printers ink in paint. So you can talk of butane used in the manufacture of carbon compound. Butane is used in manufacture of carbon black compound. Carbon black compound. Butane is used in the manufacture of carbon black compound. Then also these alkanes, they normally undergo what we call cracking. There is a subtopic we shall talk about cracking of long chain alkanes to produce short chain alkenes, hydrogen, short chain alkenes and hydrogen gas. So that hydrogen gas is used in Haber process in the manufacture of ammonia. So you will say through cracking of long chain alkanes, they produces an alkene. They produce a hydrogen. Cracking of long chain. It must be long chain. You don't just say an alkane. Long chain alkane. Long chain alkanes to produce hydrogen, which is used in Haber process. And Haber process, that is now manufacture of ammonia. When you just say Haber process, a chemistry teacher will just understand that that is the manufacture of ammonia when it combines with hydrogen and nitrogen to manufacture ammonia. So that's now the uses of alkanes. Uses of alkanes. I don't know if cracking of long chain alkanes is a chemical property, but we shall talk it later. Cracking of long chain alkanes to produce alkenes, short chain alkenes, and hydrogen to produce the Haber process. So that is now what we call alkanes. So in the next topic, we shall discuss about alkenes and we shall finalize on alkynes. Thank you for watching. I love you all.